Good afternoon, and welcome to Hand-Wavy Chemistry. Today, it's problem time, where we answer chemistry questions. The questions for today are some of my favorite to answer, as they put you in the role of a chemistry detective, analyzing different bits of analytical information to try and identify an unknown compound. This is very similar to what we did previously when we analyzed NMR spectra. But today we won't just be looking at NMR data, we will also consider other analytical techniques, such as infrared spectroscopy, which looks at the way that a molecule vibrates when exposed to infrared radiation and can be useful when identifying functional groups. Mass spectrometry, which gives us a mass-charge ratio for the molecule and can help us identify a molecular formula as well as various fragments that it can break up into. And there's UV visible spectroscopy, which looks at the transitions of electrons between different orbitals within the molecule. Now let's get started.
Here is our first unknown. We've been given infrared, mass spec, carbon-13, and proton NMR information. I want to start by looking at the mass spec. They haven't labeled many of the peaks, but what they have done for us is they have identified a molecular formula of C9H10O. Now, when I see an oxygen in the molecular formula, and I've been given the infrared spectrum, I'm going to look for what kind of functional group that could be. The frequencies associated with oxygen-containing functional groups are usually easily identified. And if we look at the infrared spectrum, we see this broad peak out here at about 3,500 per centimeter. This suggests to me that we have an OH functional group. You can see at the other end of the infrared spectrum, there are a lot of peaks. This is known as the fingerprint region, and there are a lot of different types of bending and stretching modes that can give us peaks in this region. So unless we really have to, I'm going to try and avoid looking at those peaks. So now, let's look at our NMR. I mentioned that I'm expecting to see an OH peak, and you can notice that for the peak that's slightly above 8 ppm in the 1H NMR spectrum, there is a note on it saying that it exchanges with D2O. This little tidbit tells us that this should be our OH peak. It seems to be shifted away from where we might normally expect it, but we can look and see that this NMR spectrum was done in acetone. And the position of OH peaks can change depending on what solvent they're in, as the amount of hydrogen bonding also changes. So we're going to call that peak our OH peak. Next, I'm going to focus in on those peaks around 7 ppm. This is the aromatic region and makes me think that there is probably a conjugated ring system. Something else that makes me think that we've probably got double bonds and rings is if we go back to that molecular formula, we saw it was C9H10. If we had an alkane with C9, we would expect there to be 20 hydrogen associated with it. But we only see 10. So we have 10 hydrogen missing. Divide that number by 2, we get 5. We have 5 double bond equivalents. That's either a double bond or a ring. An aromatic 6-membered ring would give us 4 of those double bond equivalents straight off the bat. 3 from the double bonds and 1 for being in a ring system. If we look at the expansions from around that region, which is this one and this one, we can see we have 4 peaks, 2 of which look like doublets and the other 2 look like triplets. This signal is indicative of and we don't know what's attached out there. But it does give us a fragment. And the reason this agrees with that kind of splitting pattern is the proton here has only one neighbor, so we'd expect to see two peaks. This next proton here has two neighbors, so we'd expect to see three peaks, and then three peaks and two peaks. And finally, because there are four distinct peaks, we know that this and this must be different. So we're now at the point where we need to think about what we have left over. We've identified an OH, we've identified a C6H4 ring system. This means we have 3 carbons left and 5 protons left, and 1 double bond equivalent left. So that double bond equivalence makes me think we have something like this. Now, I don't know which end of that would be attached to our aromatic ring, but this would be sensible. It would also use up those 3 carbon and 5 protons. Now, to try and decide which end of this propene is attached to our ring, I'm going to look at the carbon-13 spectrum, specifically the DEPT. For this spectrum, we would see peaks pointing up if it is a CH or a CH3, and peaks pointing down if it is a CH2. We see 2 peaks that point down, so there are 2 carbons that have CH2 on them. If we were to attach our propene to our ring through this carbon here, then we would have a CH3, we'd have 1 and 1. This doesn't agree with what we just said we saw in the det. However, if we attach it through this end of the propene, now we have 2 protons here, 1 proton here, 1 here, and 1 here. This is in agreement with that det assignment of there being 2 CH2 groups. Finally, we can do a full assignment by looking at the peak positions and their relative integrals. We see that the peak at 6 ppm is only worth 1 single proton. So that's going to be this one. Because these 2 protons are an alkane, not an alkene, we'd expect them to be the least shifted. So they should be the doublet down here at 3.4. Finally, we have these 2 protons. These are the peaks at 5.0 and 5.1. Because there is no rotation around that double bond, those 2 protons are actually in slightly different environments, which is why we see them as different peaks. So we can't say exactly which is which without doing additional analysis, but we know that these are these. Now let's put all of our fragments together. We have a ring system with 4 hydrogens attached to it, and we said that it was aromatic. We need an OH group, and we have our propene. And this structure makes sense based on everything that we saw in the analytical data provided to us. As a final test, an analytical chemist could perform a melting point experiment and compare the melting point of their sample to what the literature is for this particular compound. For our second question, in addition to the infrared, mass spec, carbon-13, and proton NMR we had before, we also have a UV visible spectrum. Although, to be fair, it doesn't really tell us a lot in this case. These kind of strong absorbances in the UV region are indicative of pi to pi star transitions such as we might associate with an aromatic ring system. Once again, starting with our mass spec, here we have been given a molecular formula, and once again there are oxygens present. So I'm going to go and look at the infrared spectrum and see if I can identify what type of oxygens these are. I see a very large peak at approximately 1700 wave numbers. This peak is indicative of a carbonyl group, a carbon with a double bond to an oxygen. I see two more large peaks, this one and this one. Those two peaks are in the right location for an NO2 group. And looking at our molecular formula, we do indeed see an NO2 group. If we interpret the UV spectrum information to be telling us that there is a six-membered aromatic ring system, we've basically found all of the possible atoms. That ring uses up 6 of our carbons. The carbonyl group uses up the 7th. The NO2 group uses up all of our nitrogen and our remaining oxygen. So all we have left are those 5 hydrogen. 4 of them will be somewhere on the ring, and 1 of them will be attached to the carbonyl group. And we're going to use the NMR information to determine where each substituent is. Looking at the depth from the 13C NMR spectrum, we can see that all of the carbons that have protons on them have either 1 or 3 protons attached. We know from the fragments we were just discussing that everything should be a CH, so this experiment agrees with our line of thinking. Now all that really remains is to determine the relative positions of the substituents on the ring. So for that, we're going to look at this expansion of the 1H NMR. If we have para-substitution, then these protons and these protons are in equivalent environments. So we should see just 2 peaks. So clearly this is not the case, as we can see more than just 2 peaks. Our remaining options are meta-substitution and ortho-substitution. And of the two, it is the ortho-substituted that makes the most sense when we look at the shape of that splitting. We have 2 peaks that look roughly like doublets, and then it looks like we have a quintuplet, but in reality, it's probably just 2 overlapping triplets. Putting all of this together, our final structure looks like this.
I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a question you'd like to see answered in a future problem time, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.